how do you find them? How do we discover these planets out there?
The majority of detected planets have been discovered using two main techniques, the radial velocity technique and the transit technique. So we'll see what are those techniques. So first illustration illustration 6 will show a little movie of the radial velocity technique. So with that technique, we detect the tiny movement perturbation an exoplanet has on its star. That slight movement affects the star's normal light spectrum or color signature, and the spectrum of the star that is moving toward us appears slightly shifted toward bluer and shorter wavelength, while when the star is moving away, its spectrum is shifted toward redder and longer wavelengths. So that's for the radial velocity method, and in the next movie we'll see the transit technique, how it works. And so with that technique, we measure how the luminosity of a star evolves over time. So most of the time, that luminosity is constant and quite boring. But some variable star, we will see in those variable stars that this luminosity can vary in a random fashion because of the activity of the star itself. But in some very rare occasion, we can see periodic decreases of the luminosity of that star, which indicates that one or several planets are passing in front of the star. So those techniques are what we call indirect technique, because exoplanets are detected through the indirect effect they have on their host star, but we don't actually see the planet themselves.
Well, if you're calling these indirect techniques, if we flip the coin, do we have direct techniques? Are there more direct ways to find these planets?
Some astronomers, and myself in particular, are interested in. This technique is called direct imaging, or so-called high contrast imaging. Okay. And so what is interesting with this technique is that we can actually get picture of those worlds. And this is a game-changing technique because, first of all, the type of exoplanet that we can detect with this technique is very different from the exoplanet we can detect with other indirect techniques. The second thing is that we can know exactly where the planet is and learn about the orbits of those planets. And finally, we can directly probe the chemical component of that atmosphere at different wavelengths and learn crucial information on those planets, such as their mass, their gravity, and whether certain chemical components are present in their atmosphere. So let's pull out illustration 8. Now we have only a few pictures of those exoplanets so far. And the reason is that it is pretty challenging. See, because the star is so bright that we first need to block its light to be able to see the light of the faint planet. And we're doing that by using a very small optical component that is called a coronagraph that acts similarly to what the moon does to the sun during a solar eclipse. So we can see on illustration 9 a picture of such a solar eclipse. And if you are lucky enough to have experienced a solar eclipse, I really recommend that. See if you have the chance one day. You may have noticed that we can see stars in the middle of the day. And with a coronagraph, we can do the same with any star and hunt for planets that orbit around them. But the extreme contrast of flux between the planet and its star is not the only challenge we're facing. We also need enough resolving power to be able to separate angularly the planet from the star in the image formed by the telescope. And for that, it really helps to have a big size telescope. And it also helps to observe stars that not too far from us, which limit a little bit the number of targets that we can observe with that technique. So let's have a look at the illustration 10. I would like to show you a video that illustrates how we solve the contrast issue with a chronograph. I think it's a very, very nice video. So you'll see here an exoplanetary system orbiting a star, and you want to observe that system with a telescope. So the light is going to go through the telescope, and we're going to see what's happening inside the telescope. So here, the light is going to first reach a mirror and then a couple of optics and create the image of the star on the detector. And then you have a chronograph that you put in there to remove most of the starlight. So that's one component of the chronograph, a second component of the chronograph, and you see that the light disappear. And then you can ask, but it will hide also the planet, but that's not the case because the planet is off axis and is not hidden by the chronograph. It's not blocked by the chronograph. So there are two planets in there, but we cannot see them because there are a lot of residual, instrumental aberrations in the instrument that prevent the chronograph to work optimally. So we want to correct in real time those instrumental aberrations with a deformable mirror to be able to further remove the residual speckle or residual starlight that we can see on the image. And it's often not sufficient because we also need to use and develop state-of-the-art post-processing technique to further remove the starlight. So yeah, I'm pretty sure that now that you have, you know a little bit more about how those chronograph works, you would like to see what it does in reality. I mean, what a real picture of exoplanets. So let's go to the slide 11 that shows an actual movie, not even an image, an actual movie of an orbital, an entire exoplanetary system that orbits the star HR 8799. So I think it's a particularly stunning video because you have to imagine, this is a system that is at 130 light years from us. And the HIT 799 star hosts not less than 4 giant planets that are about 10 times more massive than Jupiter and approximately the same diameter as Jupiter. And as you can see, we're pretty far from the artist concept illustration that we're seeing all the time on the internet for exoplanets. We currently don't have the capability to take such pictures, but what you have in front of you is what we can do currently, and I think it's still pretty amazing in my opinion.